Corrosion Part 2. Hello everyone, welcome to 2A Corrosion Audio Lecture 2, the Thermodynamics of Electrochemical Corrosion. The aim here is to produce equations and diagrams for predicting which corrosion process, if any, will take place in a given situation. Now, by way of introduction to corrosion thermodynamics, you may have seen the excellent 2005 King Kong remake. Jack Black in this film portrays the role of Carl Denham, a con artist who captures King Kong from Skull Island and puts Kong on display in New York, securely chained to the theatre walls so that the paying public can pay Carl Denham to come and see King Kong. So I'm sure you know that, in reality, Kong becomes enraged by this situation, and the audience starts to flee in fear that King Kong will break free. And not wanting to lose his paying audience, Denham tries to reassure them, successfully in fact, and he reassures them by saying, "Don't be alarmed, ladies and gentlemen, those chains are made of chrome steel." Clearly the implication, the public perception, is that chrome steel, which in this course basically means stainless steel, the implication is stainless steel is a very good quality material, and functionally unbreakable, so that the audience have no reason to flee the theatre. Obviously, in the film, this comes unstuck, because Carl Denham is, as well as a con artist, he's also a cheapskate, and the chains were too thin to withstand King Kong's mighty strength. But that's just a straightforward mechanical engineering failure, and we don't care about that in this course. In this course, we're looking at the earlier, much more fundamental and interesting question about how does corrosion affect our designs. And from a corrosion point of view, the chrome steel chains were an excellent choice of material. They would, in fact, have given a nice long service life if only they hadn't been carelessly overloaded by someone not doing their mechanical engineering properly. Now, stainless steel is, in many cases, a good quality material because it is often, we said last time, passive against corrosion. What we need in this lecture is a mathematical method to let us calculate whether a metal is passive in some situation, or if it isn't passive, then does it corrode actively, meaning continuously, or is it immune from corrosion, in which case it's stable forever as the metal. In order to produce an equation which answers the question, is a metal passive in some situation, or does it corrode actively, etc., we need to know what properties of the environment can cause corrosion, so that we make sure we include algebraic terms for each of these environmental properties into the equation we're going to build. Now, this example question should help us to list all of the properties which make an environment corrosive, because on this slide we have a photograph of the most corrosive place in America, namely the Kennedy Space Center Corrosion Testing Laboratory on the beach in Florida just next to the Kennedy Space Center. Now, this is obviously a nice, beautiful beach, and it has this very impressive rocket launch platform in the background, but for various reasons it's not a good place to build houses for people to enjoy the beachfront setting, and so instead, on this beach, there is a federal government laboratory. And at this laboratory, the staff put out racks of metal samples and leave them exposed to the elements, and after a few years, someone comes back, cleans off the samples, weighs them, and calculates how many millimeters or micrometers of metals have dissolved or otherwise corroded away. Now, on this particular beach, the steel samples dissolve, just bare carbon steel samples, dissolve at over 1 millimeter a year, which turns out to be the fastest corrosion rate found in any equivalent environmental lab in the United States of America. Why is that? Okay, you could stop and write a list, and if you did, I guess you would come up with some reasons like these. Most of my students start with number one and they say, the number one reason is clearly acidic chemicals, Dr. Rees, from the rocket exhaust, chemicals like nitrous oxides. And they might be right about that. I doubt those are actually the main thing, but they might contribute a bit. Really, I think the number one reason this beach is very corrosive is because, obviously, the steel is wet. Clearly, the steel samples, or coupons, are splattered with water from the ocean spray, or from the rain, pretty much all the time. And combined with that, I'd say number 2 reason, the ocean salt in this wet surface moisture on the steel contributes to the corrosiveness of the environment. On top of that, I'd say number 3, well, the steel is not only wet, but it's surrounded by oxidizing agents, mainly ocean wind from the air, which is blowing in unlimited supply from the ocean, and also maybe some of those nitrous oxides from the rocket exhausts. And if we are talking about chemicals and pollution, then maybe there's also some acidity in the moisture here, left over from the rocket exhausts too, or from some other reason. So those are the main algebraic reasons, I would say, that the Kennedy Space Center beach is very corrosive. We could probably say a few more things. We could say this is the sunshine state, so it's nice and warm, and so we mustn't forget all physical chemistry, including corrosion, gets faster with temperature. On top of that, it's very sunny, and it's also a hurricane zone. Both of those things are potentially destructive to surface coatings, and that can also speed up corrosion processes. So if we wrote a list, we could come up with several factors, environmental properties which control corrosion. And it's actually these terms which I've circled on the right which are the most important to determining whether corrosion happens and predicting how fast it happens. So those are the terms which we will want to include in an equation to say whether corrosion takes place. Okay, but what sort of equation are we going to build? If we're in the situation I've described on this beach, then fundamentally we're going to be looking at corrosion taking place underwater or on some metal which has a surface layer of moisture. That's nearly all of the cases that we'll find when we're looking at corrosion in the open environment, and also most of the cases where we'll see corrosion in the process industries. So in that situation, the presence of water means that we're looking at electrochemical corrosion, and we're going to build, that's going to be the most important situation for which we will build equations in this course. I'm skipping over, and we'll come back at the end of this course in high temperature corrosion. We'll come back to what's called chemical corrosion, which is said to take place under dry gases, or in situations where you have no water. So in that case, the thermodynamics of corrosion is actually the physical chemistry thermodynamics of metal plus oxygen giving you a metal oxide, or something like that. Now, this chemical corrosion under dry gases actually uses conventional chemical thermodynamics. So you just calculate a Gibbs energy change of reaction, and if negative, then the reaction will tend to occur. This is generally not very interesting because for nearly all metals there will be a driving force for some sort of oxidation to occur under atmospheric oxygen in a dry situation. We're much more interested for the bulk of industrial corrosion in whether electrochemical corrosion happens and how fast it happens. So we're going to have to build up a particular set of algebra for looking at that problem. Right. Page 9, section 2.2 shows the notation which is going to be used to talk about electrochemical corrosion. So, because there's no simpler electrochemical corrosion process to talk about than the one where zinc dissolves into acidic aqueous solution, I will introduce the notation of electrochemical corrosion using that simplest possible example. Zinc is easy, by the way, because there are only two phases of zinc which we need to think about. That is the zinc metal, which is the starting point, and the dissolved zinc 2+ ions, which are the end point. Our first problem is, even though this is as simple as it gets in corrosion, if we did want to use conventional chemical notation, we don't want to use this, if we did want to use conventional chemical notation, we would still need to write down at least two equations just for this simplest possible process. Those are equations 2.2 and 2.3. So equation 2.2 says that zinc metal dissolves with protons in the water. One zinc plus two protons reacts to give one dissolved zinc ion and a hydrogen molecule. That's equation 2.2. Oh, by the way, chemists don't like me for talking about protons. They like to call H plus ions in solution hydrogen ions, and they tell me off a bit for calling them protons, but I have a physics background, and I often talk about protons in this case, and I don't see anything wrong with that, so I will continue doing that in the rest of this series. Just watch out for the pure chemists. In any case, as well as equation 2.2, zinc might react with a dissolved oxygen molecule, as in equation 2.3. That shows 2 zinc atoms plus 1 O2 molecule plus 4 protons transforms into 2 dissolved zinc ions plus some water. Conventional chemical notation is, because of 2.2 and 2.3, is going to be a problem for us, because real environments contain multiple oxidizing agents, not just the natural 2 oxidizing agents in water of the protons and dissolved oxygen, but in, for example, groundwater, you might also have some nitrates, some peroxides, maybe some other metal ions mixed up as well, and we would end up needing to write down one chemical equation per oxidizing agent, calculating the Gibbs energy change, the delta G of the reaction of that oxidizing agent with the metal, and it would take ages to work out which process happens, or if the metal dissolves. Lucky for us, if we use, and this is why we use electrochemical notation, then we only have to write down one equation for the zinc dissolving, namely equation 2.4, so that's the anodic oxidation half reaction, in which one zinc metal atom transforms into one dissolved zinc 2 plus ion, and it loses 2 electrons. So equation 2.4 is an oxidation reaction because it involves a loss of electrons, and oxidation processes like this are called anode half reactions. As a shorthand notation, which you definitely need to learn so that you can write about these processes more compactly, equation 2.4 is written in electrochemical notation as shown in 2.4a. So it's zinc, vertical line, zinc 2 plus. So this is a very important shorthand for you to learn, because if you want to write about the rate of a corrosion process, then just a very small part of that, you'll need to write down the rate of the dissolving zinc electrode. And if you use the equation, the notation in 2.4a, you can very quickly write down something like equation 2.5, which says that the reaction rate is 1 mole of zinc per centimetre squared of its surface per year. And then later in chapter 3, we'll see that that rate in equation 2.5 can actually more usefully be written as equation 2.6, in which case we're going to say the rate is a current density, or small I, of 6 milliamps per centimetre squared. So these shorthand notations are important. They're going to speed up your ability to write down the algebra of corrosion, which means that you can write down more detail about the processes, which is important. In order to have this benefit of just one half reaction for the zinc dissolving, obviously we needed to separate out the half reactions for the other reagents. In this case we separate them out as equation 2.7 for the hydrogen ions and equation 2.8 for the dissolved oxygen molecules reacting. So those species are oxidizing agents, and they undergo a reduction reaction. The notation to look at their half reaction on their own, is shown below them as 2.7a and 2.8a, respectively. In both cases, and this is because we're looking at a single half reaction, we have the reduced species on the left, like H2, a vertical line to show the transition into the oxidized species on the right, like H+. So separating out this notation is done for 3 reasons in corrosion science, which should make perfect sense by the end of the course. The first is that it's realistic, the second is that it's simpler, and the third is that it's a more useful notation if we want to make powerful mathematical predictions of what happens in some situation. So let's take these in turn. So realistic. Real corrosion processes actually do take place in separate locations, as shown by the electrochemical notation. For example, if you have a steel boat, a steel ship, maybe some metal at the bottom of the ship dissolves into the ocean water, but it's actually very likely that the, say, dissolved oxygen molecule which balances out that process, that reaction of the oxygen may well happen several meters away on the side of the boat near to the surface of the water. So it would be wrong to write corrosion processes like equation 2.3 as a molecular collision. So that's because if we wrote zinc plus oxygen gives this dissolved zinc plus ions and then balance it out and the oxygen turns into water, that doesn't take place as a single collision in one location. It really does take place in separate locations, as implied by the equation 2.4 and 2.8, say, taken separately. And there is electron transport between them. It can be over a long distance. As well as being more realistic to write corrosion as this two separate electrochemical half reactions, it's actually going to make our life simpler. It will simplify our maths because now we only have one equation per metal. We just have the zinc dissolving to zinc 2+, and although it's true that we still have several, maybe n different oxidizing agent half reactions, those have all been separated out. And it will turn out that often, instead of dealing with them mathematically, having to deal with n equations, we can actually make one easy measurement which works out their average effect, and we only need to consider our zinc metal and the one measurement. We no longer need to consider n different equations. So it will turn out that our life is made simpler by using electrochemical notation. Our mathematical powers are also made more profound. It will turn out that the electrochemical notation is better for making predictions of rate. So I will come back to this in the section on kinetics, but many corrosion processes are limited by, for example, the ion conductivity of the water or the solution which the process is taking place in. So one of the reasons seawater is very corrosive is because it has a high ion conductivity. And when we need to write down equations to work out what this speed of corrosion is, it will be easier for us to combine electrochemical corrosion equations where we have unbalanced half processes where there's electrical charge in the form of electrons leaving the process. It will be easy to join them up with kinetic limitation equations where the process might be slowed down or rate limited by the effect of ion resistance in solution. So it will be simpler, more realistic, and predictively more useful for us to deal with electrochemical notation. Okay, so page 10, figure 2.3.1 shows the physical picture which is referred to whenever you see electrochemical cell notation. So that we have the notation for an individual anode, like the dissolving zinc, and we have the notation for an individual cathode. The simplest possible corrosion process is what is shown in this diagram, and the simplest possible process involves those two electrodes in ion contact. That's what the solution with the salt bridge between the two beakers provides. It's ion contact between the anode and the cathode, and the anode and the cathode are also in electrical contact. So in this idealized picture, the electrical contact is shown as a load with possibly some potential difference across it. That isn't always there physically. Sometimes you might be looking at a single piece of metal which has both the anode and the cathode on its surface, in which case the load in this idealized picture corresponds to an almost zero resistance, and there would be not much potential difference between the anode and the cathode sites. But in general, when we think about electrochemical processes, it's helpful to separate them out, as shown in that diagram. When we show these diagrams, we could draw that, and we could say this takes place at 298 kelvins, pH 0, and the dissolved zinc 2+ ion concentration is 1 molar. and if we did that, we would have completely described the process. But it's much better to write down equation 2.9 instead of drawing the diagram, and just next to equation 2.9 have the description of what is the temperature of the system and what are the two concentrations relevant to this. So pH 0 gives you the H plus concentration, and we also need to have written down the zinc ion concentration. Okay. So equation 2.9. This is the way that we would write the electrochemical notation for the complete cell. So this time we have the same bits as before. We have the individual anode on the left and the individual cathode, which we're considering protons turning into hydrogen. The cathode is on the right. In this case, we actually have the cathode written with oxidized species on the left and then reduced species on the right. That's because when we're talking about a complete cell, we always think about the chemical reaction going forwards by species moving from the left-hand side to the right-hand side of the vertical lines. And the double vertical line means that we have a separate anode and cathode. It means that separate ions are taking part in the anode process and the cathode process. The double vertical line looks a bit like a tube, and it represents the salt bridge or capillary tube, which is shown in the diagram figure 2.3.1. The salt bridge is simply a long distance in the solution, so that this means that if the zinc dissolves into solution, it doesn't find its way to the cathode, not anytime soon, so that we don't have to worry about zinc ions taking part in the cathode reaction. So the salt bridge means that we have separation of the two processes. Let's have a look at a few examples of this. So on the following page we have first example of a cell which would not require a salt bridge. So we can imagine if we do some copper plating, we might have one lump of copper which we're dissolving. We're using a current to drive this process, dissolving some copper into a bath of copper sulfate solution, and some object which we're plating, the same copper plates out. So in that case we would have this notation 2.12, which shows the driven copper electroplating process, and you have the copper and the copper 2 plus forming the left-hand side. That's the anode. That's some copper you don't care about, which is being deliberately dissolved. And then the right-hand part, copper 2 plus to copper metal, that represents the plating side onto something which you're trying to put copper onto it. The electroplating bath requires a power source, a driven current to force the electroplating to take place. Equation 2.13, with the picture shown next to it, shows you a concentration cell where you could do copper plating in this situation without using a supplied electrical current as a power source to drive it. The reason is, in this situation we say we have an anode on the left, which is copper metal dissolving into some dilute copper sulfate solution. I have this magic salt bridge, which means that we don't immediately have rapid mixing with the concentrated copper sulfate solution on the right, and it's from the concentrated copper sulfate solution that we expect copper ions to plate out onto the cathode, or some object which we want to electroplate. So the way the concentration cell works for plating is that there is a net driving force for the overall process, that is, dissolution into dilute solution combined with plating from concentrated solution. The net driving force for the concentration cell electroplating is obviously there because the process overall has the same change of state as if copper ions were to move by diffusion from the concentrated solution to the dilute solution. We know there's a net driving force for that, and so there is the same driving force for something which has the same change of state, which is the concentration cell electroplating process. So that one's fairly straightforward to understand. Equation 2.14 shows an example of a slightly more complicated to write form of electrochemical cell. Here we have a battery with zinc metal dissolving at the anode, and the cathode is silver chloride, which is reduced to silver as the system supplies some energy. So the interesting thing, well, the thing we need to know about the notation there is that we're using a comma to separate zinc 2 plus ions and Cl- ions in the electrolyte of this cell. Well, we don't have to in this case. We could write it as zinc chloride aqueous, as in 2.14a, but sometimes when we need to show that there are multiple species, multiple dissolved ions in solution at the same time, in principle in contact with the same electrode, then we can do that using a comma to separate them out. Good. And equation 2.15 shows an example of a way the hydrogen electrode is written in electrochemical notation. The hydrogen electrode is hydrogen molecules, H2 molecules, dissolving to H+ ions in solution. In equation 2.15, we have that process going on. You see there's that as an anode. We have hydrogen gas in the middle and H+ ions on the right. We have on the far left, though, we have platinum. So that's just there to tell you that this process is taking place on a platinum surface. That's important because when we get to kinetic models, the speed which processes take place at depends on what metal a process might be taking part on. So especially when we're dealing with the important hydrogen reaction. Good. Now let's look at what is cell notation used for. So cell notation, the important thing for you is that it's used to, in a compact way, allow you to refer to or to describe a cell in algebraic notation. So I'm going to read you a paragraph, and then we're going to say that whole paragraph you don't want to write, you just want to write equation 2.16, the cell notation, inside a bit of algebra, and one line underneath it saying that it's pH 0, 1 bar absolute with a particular dissolved silver ion concentration and 25 Celsius. So, writing down equation 2.16 will allow us to convey the same information that we have in this entire paragraph. So we say, imagine a cell, a complete corrosion cell, as in figure 2.3.1. It contains hydrogen gas dissolving at the anode and silver ions electroplating onto silver metal at the cathode. All of the species have unit activity, which means pH 0, activity of silver ions is 1, the temperature is 25 Celsius, and then we're told it is found that the potential difference between the electrodes, delta E, is 0.799 volts, and that this potential difference is an electromotive force that is able to supply energy to the load. So all of that paragraph is embodied by equation 2.16, the algebra there, where I've said the delta E, that's the cell potential difference of the process described inside the brackets using the electrochemical cell notation, the delta E is plus 0.799 volts. So the plus tells us that it's an electromotive force, that it could supply energy, and the notation tells us everything else in the paragraph. And just below the algebra notation, we just note down the concentrations and temperature. This is going to be important because electrochemistry and thermodynamics requires us to write several lines with some manipulations on this. So 2.16 has the same meaning as the paragraph above it. As an aside, equation 2.16 is actually describing a special situation. Because we were at 25 Celsius and unit activities, and I put the hydrogen at the anode, this situation actually describes the standard electrode potential of the silver electrode. So if you see this E superscript circle of just the silver electrode notation, and you're told that that's plus 0.799 volts SHE, then that's telling you that if you were to set up the whole cell in the paragraph above with equation 2.16, if you were to set that up, the fact that the cell gives you an electromotive force of plus 799 volts is the same as telling us that the standard electrode potential of the silver electrode is this plus 0.799 volts SHE. Good. Naming convention for anode and cathode. Just to make sure we've said this, the anode is the site where an oxidation reaction takes place. That's something which loses electrons. So please do not make, please, the common mistake of labeling one terminal of a battery in your diagram as the anode. Okay, not just based on its physical location or material. Whether something is an anode depends on what chemistry it's doing. So the fact that something is zinc, in some situations it might be an anode, in other situations it might be being driven as a cathode somehow. In particular, in equation 2.16 we have hydrogen labelled as the anode on the left-hand side of the cell notation. So the hydrogen is dissolving to hydrogen ions, and silver ions are plating out at the cathode. If I were to, and this is potentially supplying us with some power, acting as a battery, if I were to recharge this battery by forcing a current to travel backwards through it, using some sort of external power source, then I could get the silver to dissolve, and in that case my notation would be reversed and I would have silver at the anode. So the important lesson is that it's not the identity of the material which tells you whether it's an anode, it's the identity of the material and what it's doing. That's very important for us. Section 2.5, because corrosion pretty much exclusively is something which is taking place as an anode process in an electrochemical cell. Virtually every problem in corrosion is either like equation 2.17, some metal dissolving into solution, or it's like equation 2.18, some metal turning into a solid oxide or hydroxide. Those are the main two ways that our metal objects in chemical engineering will be lost to us, or will have their properties deteriorate because the oxide is not as good as the metal for whatever we want to do. And both of those are anode processes. The metal is increasing its oxidation state. There are just a couple, and they're special, so they're worth mentioning, a couple of corrosion problems which do involve the cathode of a cell. One is hydrogen embrittlement, so if some metal like zinc dissolves, and at some cathode somewhere hydrogen gas is produced, hydrogen gas is a big bugbear of the process industries, because allegedly it can dissolve into steels and it can embrittle the steels. So hydrogen embrittlement is something which might happen at a cathode. Normally if we have a cathode, we'll be happy enough. We're not going to be losing metal, but we could be getting hydrogen embrittlement. And in a different kind of system we could have something called deposition corrosion. That's a problem in recirculated water systems. We'll come back to it in localized corrosion phenomena. Basically, sometimes metal plating out of solution leads to further problems. It will be a bad source of problems for when we have copper able to plate out onto aluminium, because that can cause some subsequent problems down the line. But basically, in this course, my question, does corrosion happen? We're going to translate this into, does the electrochemical cell proceed with metal at the anode? Okay. So this is excellent. This gets us halfway to answering the question of the chapter, does corrosion happen? We now need to look at section 2.6, in which we're going to translate the physical chemistry answer, or method of answering does a process happen, into the electrochemical process of answering does the process happen. And the process we're going to be worrying about is, does a cell reaction take place with our metal of interest at the anode? So consider the electrochemical cell that we're talking about, the zinc dissolution cell in acid, equation 2.19. So we know, we're going to take as a starting point in this course that we can do physical chemistry, and so we understand that if I wanted to know in physical chemistry terms, does this process happen, and I don't care about any other possible oxidizing agents, I would just look up the standard Gibbs energy change of reaction. That's equation 2.20, and I'd say this is a very big negative Gibbs energy change, minus 147 kilojoules per mole of zinc. Therefore, I expect that this zinc dissolving in acid really definitely does happen. And that's all I would need to do. If it was at standard concentration, I would just look up the standard Gibbs energy change. If I was at non-standard concentration, then I would have my Gibbs energy change would be the value at standard concentration plus a correction RT log of QR, where QR is this reaction quotient term to do with species concentrations or activities in equation 2.22. In this course, we will be using the assumption that activity of a species means concentration in moles per decimeter cubed for dissolved species. Likewise, we'll probably assume unit activities for other things such as pure solids, mostly pure water. Hydrogen gas will, if it comes up, we'll probably assume is at 1 bar, and we'll just take that as having unit activity. So that's what we'll be doing in this course, or anyway, you'll be told what activities are for, say, hydrogen gas if it's relevant, but the important thing is solid phases you assume have unit activity. Okay, so these physical chemistry equations 2.20 to 2.22, I'm not going to derive in this course. If you want a refresher to look up where they come from, you can either look up Atkins' Physical Chemistry, I think it's chapter 9.2 in the 5th edition, or you can look up Zaki Ahmad's book, chapter 2, has some derivation of these equations. But we're going to take them as a starting point, because I want to translate these into electrochemistry. So, given that we're happy with these, what are we going to do? So we're looking at, does a process go forward? A purely chemical process goes forward spontaneously if the Gibbs energy change, the delta G of reaction, is less than 0. And it would be a reversible process if the delta G of the reaction was equal to 0. So delta G of reaction equal to 0 is important because we can use it to find conditions where some purely chemical reaction just begins to go forward. In our work of electrochemistry, we're looking at a cell process, which involves the chemical reaction plus some electrical charge flow between the electrodes. So therefore, the total Gibbs energy change of an electrochemical cell includes some electrical work, as well as the reaction. And we can write the total Gibbs energy change in an electrochemical cell as equation 2.23. It's delta G of reaction, plus some, I've written it as plus some delta work electrical, some work done on the load by the cell process going forwards. So we can then use the same logic that we had before. An electrochemical process will go forwards reversibly if the total delta G, the total Gibbs energy change, is negative, and it's reversible if the total Gibbs energy change is 0. Importantly, we can make, or you can easily imagine making an electrochemical cell operating reversibly by controlling the electromotive force which is drawn by the load. So, in a reversible electrochemical cell, therefore, we'd say that we have total Gibbs energy change is delta G reaction plus work electrical is equal to 0. And the electrical work, we're going to say electrical work in this cell, according to equation 2.25, is just equal to charge times voltage. So the voltage which we're interested in is this E of reversible cell. E is a voltage in this course, or a potential difference. So E does not mean electric field, it means potential difference. Because this course is a thermodynamics course, V for V is already taken up by volume, potentially. So we use E to represent volts, or potential difference. Assuming the cell has negligible ion resistance and is operating reversibly, the electrical work on its load is then given by this equation 2.25. Work electrical is charge times voltage. The charge is ZF. That's the amount of charge moving when 1 mole of zinc dissolves, and the voltage is this E of reversible cell, whatever the reversible cell potential happens to be. We can use this equation 2.25 to identify this important thermodynamic term, so we get a very important relation, equation 2.26, which tells us that the Gibbs energy change of the reaction in the cell is equal to minus ZF, that charge, times the voltage, the E reversible cell. This allows us to tabulate E reversible cell. What does it mean physically? Well, a cell is reversible, essentially, if all the Gibbs energy change of the reaction is converted into useful electromotive force. And this value of this E can be measured in practice. If you have your cell like shown in diagram 2.3.1, you could simply place a voltmeter between, and no resistor, just the voltmeter between the two electrodes, and there would be a negligible current flowing through a high impedance voltmeter, and it would simply measure the potential, the reversible cell potential. So as long as you can imagine separating your electrode reactions, and we can always imagine separating the electrode reactions, we can in principle measure the reversible cell potential very easily. And it's going to be important for us because what is the reversible cell potential difference is going to be our criterion for whether corrosion happens. So remember, pure chemical reactions went forward if the Gibbs energy change of reaction was negative. In electrochemistry, we have the same thing in principle. The corrosion process proceeds spontaneously if the Gibbs energy change, the total Gibbs energy change of the system is negative, but what we write this as is the corrosion proceeds spontaneously if the reversible cell potential is positive, in other words, if it could supply some work. Okay, so then let's do an example of let's do an example problem. So we have 2.6.1 example, converting thermodynamic data from physical chemistry into reversible cell potential. So the question is, what is the electromotive force, or potential difference, exerted by the following zinc acid cell when it's operated reversibly at pH 0 with a dissolved zinc 2+ concentration of 1 molar? So we have the cell notation shown in the example. And we have, then the question is, how do we take that Gibbs energy change, which we're told under these conditions? The conditions are actually standard conditions, so the Gibbs energy change of the reaction is the minus 147 kilojoules per mole we presented earlier as the standard Gibbs energy change. We just use equation 2.26. E of reversible cell is equal to this minus delta G of reaction over ZF, plug numbers in, and the E of reversible cell for zinc dissolving. The reversible cell potential is plus 0.76 volts. That's good. Because it's positive, that means that zinc dissolving in acid is predicted to be a process that does go forward, according to electrochemical thermodynamics. As it should do, because of course we definitely know zinc really does want to dissolve in acid. Good. Now at this point we need to define standard electrode potential, so this is page 14, section 2.7. Standard electrode potential is a subject we've been dancing around so far, but we need to define it very precisely. So it's best to do that by continuing with our example of zinc. So the standard electrode, I'm going to in fact read this text because thermodynamics is often such a precise subject you just have to read the text. So I will largely be quoting at the moment from this bit of the notes. So for zinc, standard electrode potential can be defined as follows. It's the value of this reversible cell potential in a special case. The standard electrode potential of the zinc electrode, this is denoted in algebra by E superscript circle and then brackets around the zinc electrode notation. It's defined as, the standard electrode potential is defined as the value of the reversible cell potential difference if we have set up a cell with a zinc cathode, that's the zinc, a cathode means that zinc ions are plated to zinc metal, and a hydrogen anode. And in this cell all the reagents are at unit activity and the cell is operating reversibly. That means fairly slowly. Thermodynamically it's a bit more precise than fairly slowly, but you imagine this cell is just going forward at a negligible rate because we've controlled it to make it reversible, and all of the free energy change of reaction is being drawn out by the load. Standard electrode potential is usually defined at 25 Celsius. The units of standard electrode potential are in volts, and they should be written as volts subscript SHE, which makes clear that the anode is a standard hydrogen electrode. That's important because if you look in equation 2.27, the term on the left-hand side, this E superscript circle of the zinc electrode, this does not mention hydrogen in its notation. So the fact that we have volts, we need to make it sure that it's written volts SHE for volts standard hydrogen electrode. The unit volts SHE reminds us to how this definition of the standard electrode potential is completed. It's by saying that according to the top line of equation 2.27, your standard electrode potential is the reversible cell potential difference of this specific cell at unit activities, and then we use equation 2.26 to translate from the Gibbs energy change, or the standard Gibbs energy change of this cell, into the standard electrode potential. So the reaction taking place in this standard cell is zinc being reduced by hydrogen, because we said zinc was at the cathode. Now, as we know, in nature, dissolved zinc ions are not naturally going to be reduced into native zinc metal. You don't find deposits of zinc metal lying around the world, and that's consistent with this. This reaction has a negative value of its reversible cell potential. So the zinc has a negative standard electrode potential. That's consistent with the process not going forwards spontaneously in nature, and in other words, zinc is naturally found in oxidized forms. Remember, our criterion was a process goes forward if its reversible cell potential difference is positive. All of this standard electrode potential is very important to understand so that we can do some further manipulations to look at more general electrochemistry. So in section 2.8, this is an example of how we use standard electrode potentials. So we're now thinking about some general purpose process. So 2.28 is an electrochemical cell where I've got a block of metal, zinc metal dissolving, and the charge for that is balanced out by some copper, maybe some copper sulfate solution. The copper ions of that are plating out onto a strip of copper somewhere. The reason we need to use standard electrode potentials to study this is because I want to know, does this process go forwards? Well, it does, because I know basic chemistry and I know that's a displacement reaction that will very happily happen. But why does it happen in electrochemistry terms? Well, the process of zinc dissolving and copper plating out involves materially the same change in state as this expanded form 2.29, where on the first term copper plates out while some hydrogen gas is used up as the anode, and on the other side of 2.29 the zinc dissolves and an equal amount of hydrogen gas is made. 2.29 is materially the same as 2.30, because to go from 2.29 to 2.30, I've just said adding the forward process involving the zinc is the same as subtracting the reverse process. And that's true in terms of the overall change of state, so that's perfectly fair manipulation of the algebra. Because the change in state is the same for equation 2.28 as 2.30, that means the Gibbs energy change of these reactions are the same. And so I get an expression for the Gibbs energy change of the process I'm interested in, 2.28, and my expression for this change is 2.31 equation. If I take 2.31 and I divide it through by charge, ZF, that's ZF coulombs per mole of zinc being processed, and let's also introduce this superscript circle to remind us that we're at unit activity, then I get equation 2.32. This tells us the standard reversible cell potential difference for this complicated process that involved zinc and copper is just equal to the difference in the standard electrode potentials of the copper and the zinc. More generally, the point is that we could have done this for any processes we wanted to. We could have referred any two electrodes, we could have expanded them, adding in this dummy hydrogen electrode, and then we could have said the reversible cell potential difference for anything where we have some anode and some cathode it's equal to this. It's equal to the standard electrode potential of the cathode minus the standard electrode potential of the anode. This is super, super important. So this is the most important part of the thermodynamics of electrochemistry. What we have there is a method for measuring whether the reversible cell potential difference of any process is positive. In other words, we just need to know the difference in standard electrode potentials of the possible anode and the possible cathode. And if it's positive, when the metal we're worried about is the anode, then we potentially do have corrosion happening. If it's this is if it's at standard concentrations. So everything between 2.28 and 2.33 I've derived for predicting will a metal corrode at standard concentrations. At non-unit activities, it's a little harder, but we only have to add a correction term. It turns out that the Gibbs energy changes are just different, but by an equivalent expression, we can find an equivalent expression as 2.33, which we can use in any case, and then we're looking at the 2.34 equation. So we're looking at reversible cell potential difference is now equal to some equilibrium potential of the cathode minus an equilibrium potential of the anode. The difference between 2.34 and the previous equation 2.33 is that in 2.33 I had superscript circles in the algebra indicating unit activity, and in 2.34 I have subscript zeros next to my E terms, which represent equilibrium but not necessarily at unit activity. So it will turn out we can get this simple expression for what is the reversible cell potential of some process, and it's just the difference between the standard electrode potential of the cathode and the anode. Now, the anode term we can look up. I said there's one equation I want to worry about, that's does the zinc dissolve. So we need to look up the one equilibrium potential of the zinc. The cathode reactions, on the other hand, I said there might be several in the real world, and they might not be that easy to deal with. But that doesn't matter, because you can see in equation 2.35, what I've done is I've simply said we can measure the equilibrium potential of the cathode on whatever metal we have in our environment. That we just need to use one measurement with a voltmeter connected between a standard hydrogen cell, in principle, and the unknown cathode that we're looking at, and then we know the cathode equilibrium potential. And then that means that with one measurement and one equation, 2.34, we can calculate whether a metal in any case corrodes. Do excuse my coughing, sorry. Now, the thermodynamics on pages 12 to 14 is very important, so do stop and read through that. Thermodynamics is probably easier to learn from writing on the page than it is from discussion out loud, just because of the amount of things which are important, which you have to take away about the notation of what's going on. So do read the derivation in part 14, and please do be aware it's very important because it allows us to make a calculation as to whether any metal corrodes, dissolves, say, and all we need to do is look up one number, the standard electrode potential for the metal. We maybe need to calculate a correction to its equilibrium potential if it's at non-standard concentration. And we need to do one measurement of the environment, or we need to do one measurement representing the average effect of all the oxidizing agents in the environment. So this means that we succeed in what we wanted to do. We have a simple method for working out whether corrosion happens. Okay. Page 15 recaps the same idea again. So there it is, at the top half of the page there's the formal IUPAC definition of standard electrode potential. And in section 2.9.1 there's a section about practical measurements of practical measurements of electrode potentials, such as the cathode potentials we wanted to learn about, the average effect of all the oxidizing agents in the environment. So those measurements are done in practice using not a standard hydrogen electrode as our reference from which to measure, but instead typically using something like a silver chloride electrode, which is much easier to manufacture. It's just a silver wire which has been put in some hydrochloric acid for a bit, and then that's it. You can just stab that into the ground and that's your reference electrode. Those are easier to work with, and the equations 2.37 to 2.39 use the same manipulation as on page 14 in order to show how we can measure an electrode potential of something relative to standard hydrogen electrode by actually measuring it relative to a silver chloride electrode, and then adding the difference between the standard hydrogen electrode and the silver chloride electrode. So that's how measurements of electrode potential are done in practice. Next time, we'll look at how this method can be adapted to answer the question, does corrosion happen in any situation, including when we have non-standard concentrations, like in the case of a copper barrel possibly dissolving in seawater. Okay, so I will see you for that in the future.